Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at how we can take full mass ratios to determine real chemical formulas. Specifically, we're going to aim for the simple form of empirical formula. So if I will go ahead and have a mass composition, which is fairly easy to measure experimentally, how can I figure out the empirical formula? So you can do this with essentially four simple steps. So the first is you're going to need to convert all of the data or masses you have into moles. So if you don't have masses and instead you have percent masses, go ahead and use a convention. Assume that we have a total of 100 grams of the molecule of interest. Then, with these individual moles of each species, we can calculate a tentative formula. So essentially, you can list all of the species present and their relative ratios. Then from there, divide all of the subscripts by the smallest subscript. This means that at least one of your subscripts should be a value of 1. Everything else should be larger. However, some of those numbers may not be a whole number. So multiply all your subscripts by any number that you need in order to obtain a whole number. So for example, if something ends in 0.33, you're probably going to need to multiply by 3 to make sure that everybody's a whole number. If you have a 0.25, multiply by 4, and so forth. So let's go ahead and work an example, because this is a little messy. So let's say I've got glucose. It has a mass composition of 40% carbon, 6.67% hydrogen, and about 53% oxygen. So I need to go ahead and find the moles of each. So what we can do is simply use the molar mass of each of these elements. So I can take that 40% of carbon and say that's 40 grams of carbon, or about 3.3 moles of carbon. That 7% oxygen becomes 7 grams hydrogen, which then becomes a little less than 7 moles hydrogen. Gotta love 1-to-1 ratios. Finally, we have about 53.3 grams of oxygen. Use the molecular ratio, it's 3.3 moles of oxygen. And you'll note that just like we found last time, we have an equal number of moles of carbon as oxygen present. So what we can do is take these number of moles of each species and put it together in terms of our tentative empirical formula. Well, this ain't very pretty, so we're going to divide all of these numbers by the smallest one. In this case, 3.33 is our smallest number, even though it's shared by two different elements. So I'll divide everybody by 3.33, and we end up with C1, H2, O1. Note that this is actually the same empirical formula as both formaldehyde and acetic acid. Wow, this is a really common one. And yeah, you'll find it's very common in a lot of biologically produced molecules. Now, all of these numbers are whole numbers, so we don't need to multiply it. And we do have an empirical formula of 1 to 1. However, it is worth noting the true molecular formula is C6H12O6. However, the only way to go in between these two is if you know how many moles of the total molecule are present based on for the amount of mass of molecules that was used. And in order to do this, we need to know a little bit more about how gases work in order to make that full conversion. But for now, we're going to satisfy ourselves with knowing that the true molecular formula is 6 times the empirical one. Now, here's kind of a good question. How do we get these percent masses? In practice, a lot of chemical formula are determined through something called combustion analysis. So the basic idea of combustion analysis is you can feed in any sort of molecule, typically they're carbon rich. You put in a stream of oxygen under high heat, and all of the carbon will end up producing CO2. All of the hydrogen will produce water, and any additional molecules will make their own things. But we'll talk about that a little bit more next chapter when we get to combustion. But essentially what ends up happening here is that we can then isolate all of the CO2 and the water to find the mass of water and CO2 present. And by knowing the mass of the initial mass of our sample that we fed in, and the mass of hydrogen present in water and carbon present in oxygen, because again, we know their molecular formulas, we can essentially determine the mass of each of the elements and the total mass. Any, any deviation in between the mass of hydrogen, carbon, and the total mass should be the oxygen that came in with the molecule. And you can then use this to determine the empirical formulas, just like we described. So this kind of brings us to our end of playing with the chemical formulas. We're going to try and put them to a little bit more use next time. Until then, take care.